In our last video, we looked at the basic functionality of a bipolar transistor and explained a short design example of an AC-coupled emitter follower. But if we want to fully understand the complex behavior of transistor amplifiers, we have to go a little bit more into detail. So stay tuned as we go a level deeper and address the limitations of transistor amplifiers and find out how to cope with them. For all our videos, you can find some additional links in the video description. Feel free to pause anytime and have a look at it if anything is unclear during the video. So let's pick up where we left off in our last video by considering the emitter follower. We already know that we have to bias the voltage at the base in order to not run into trouble with clipping. We also know how to calculate the component values to be able to amplify a small alternating signal. But this circuit will only amplify currents. If we want to amplify a small AC voltage, like a microphone signal, we first need to transform the output current IE into a voltage. And what's the easiest way to transform a current into a voltage? Yes, we need a resistor. If we simply add a resistor at the collector of the transistor and move the output to the collector, we can build ourselves a basic voltage amplifier, which is also called the common emitter amplifier. Now let's assume that we have already biased the input so that the output voltage is half of the supply voltage. This should guarantee the largest possible output swing for a small AC signal at the input. Now imagine a small AC voltage delta VBE at the input of the amplifier. The emitter will follow the change of the voltage so that delta VE is equal to delta VBE. This will cause an alternating emitter current delta IE, which can be expressed as the alternating emitter voltage delta VE divided by the emitter resistor. Since the AC voltages at the base and the emitter are the same, we conclude that delta IE is delta VBE divided by the resistance RE. The changing emitter current, delta IE, causes nearly the same change in collector current, delta IC, and therefore a changing voltage at the resistor RC, which leads to a changing output voltage, delta VC. And there we have it, a voltage amplifier. We now only want to consider the alternating values of the circuit, since the signals we want to amplify are AC signals. It is common to describe the alternating values with small letters. If we look at the output voltage, we can see that the rise in IC causes an increasing voltage drop at the resistor RC, and therefore a decreasing voltage at the output. So we can write Vout is minus IC times RC. Or, if we insert the formula above, we get Vout is minus VB times RC divided by RE. We can also define the gain of the circuit very easily. By dividing the output voltage by the input voltage, we get the gain of minus RC divided by RE. Neat, isn't it? We can simply define any gain only by adjusting the values of the two resistors RE and RC. If we use, for instance, 10K for RC and 1K for RE, we get a gain of minus 10. But wait, that does seem a little bit too easy. What if we would make RE 0 ohms? According to our calculation, the gain of the circuit would become minus infinity. That can't be right. If we set up a test circuit to do some measurements, we will quickly see that the gain usually does not reach values anywhere close to minus 1000. We also find that the amplifier has a nonlinear behavior if the emitter resistance becomes zero, which means that the output signal will not look at all like the input signal. We would also notice that the biasing changes with temperature. So clearly there's something wrong with our simple transistor model. Maybe it needs some modification. In order to get a better understanding of the behavior of the bipolar transistor, we have to do a variety of measurements. So let's consider the following measurement arrangement to derive some dependencies of the transistor. The circuit consists of an NPN transistor and two variable voltage sources to control the base emitter voltage VBE and the collector emitter voltage VCE. For our first measurement, we keep VCE constant and slowly raise the base emitter voltage VBE. We measure the base current IB as we do so and get to the so-called input characteristic of a bipolar transistor. You may recognize this characteristic as the behavior of a forward-biased diode, which makes a lot of sense if you remember the simplified diode circuit from our last video. If we do the measurement again for different positive values of VCE, we will see not much difference in the behavior. If we also measure the collector current IC for different values of the collector emitter voltage VCE, we can determine another function called the output characteristic of the transistor. The diagram only shows the characteristic of 5 different base currents, but in reality there are infinitely many values for IB, which would result in infinitely many curves, which again would not make much sense to draw into one diagram. Last but not least, we can measure the output current IC as a function of the base current IB. This way we get the so-called transfer characteristic of the transistor. This function varies quite a lot with different values of VCE. To keep it easy, we will not go into detail at this point. Just keep in mind that the output current does not always change linearly with the input current, especially when the input current is very small or very high. Now let's explore the usefulness of these 3 graphs we just derived by considering the voltage amplifier circuit from before. For the sake of simplicity, we make the emitter resistor 0 ohms by connecting the emitter directly to ground. Now our output voltage is simply the collector emitter voltage VCE. We know that we can adjust a constant quiescent current IC by adjusting the biasing voltage VBE with the voltage divider at the input. By doing so, the voltage at the collector resistor VRC will attain different values according to the quiescent current IC. Since the total voltage VCC is fixed, the output voltage VCE will also vary with different quiescent currents. When we adjust IC to be high, VRC will also be high and therefore the output voltage VCE will be low. The theoretical maximum of IC is represented in our diagram by this point. If the transistor is switched off, which means that IB is basically 0, no current IC will flow and the output voltage will be the supply voltage VCC, which is represented by this point. To sum up, we can say that by adjusting the voltage divider at the input, we can adjust the quiescent current IC basically anywhere along this line and therefore define a quiescent point. Now let's look at our 3 characteristics from before. If we combine all 3 diagrams, we have found a wonderful way to describe the behavior of our common emitter amplifier. First, we have to find an operating point, also known as bias point, quiescent point, or in short, Q point. As we already know, we simply have to adjust R1 and R2 to get a voltage drop at the base somewhat over 0.6 volt. This leads to a base current IB, which again leads to a collector current IC, and finally to a steady state output voltage VCE. In a second step, we can amplify a small AC voltage delta VBE at the input, which leads to a corresponding AC current IB at the base, an amplified AC current delta IC, and finally an amplified voltage delta VCE at the output. By using this representation of the behavior of a transistor, we can also see what happens if we choose our biasing point wrong. If we choose the biasing voltage at the input too low, the transistor will cut off the output voltage because the base emitter diode stops conducting. But we also cannot choose the biasing point too high, because we would end up with the maximal collector current. At this point, the output voltage cannot go any lower and the transistor is in saturation. The minimal voltage drop at the output is never zero though. It depends on the transistor and lies between 0.05 and 0.2 volts. The nonlinear characteristic curves put also a limit to the maximal amplitude of the input signal because it gets distorted at the output. So what does that all mean for our calculations? How we should account for the nonlinear behavior of the transistor if we want to build a working voltage amplifier? Well, let's go back a little and look at our set of rules we discussed in our last video. The first two rules still seem to hold true. The important change is in rule number 3. For a basic calculation, the rule might be sufficient, but if we want to account for a nonlinear behavior of IC, we will need a more sophisticated formula. As we now know, IC is not only dependent on beta and the base current, IB, but also on the base emitter voltage, the saturation current, and, to make things even worse, the temperature. Without going too much into detail, we get a new equation for our collector current, which is called the Ebers-Moll equation. It is derived from this more complex model of a bipolar transistor. If you want to know more about the Ebers-Moll model, you can find some links in the video description. For now, we are happy with the simplified version of this equation, which will suffice for all our purposes. It accounts for all major dependencies of IC, like the base emitter voltage VBE, the saturation current ICS, and the temperature, which is expressed by Vt. Vt is defined as the Boltzmann's constant K times the absolute temperature T in Kelvin divided by the electron charge Q. At room temperature, Vt has a value of about 25 millivolts. From this equation, we can derive a simple but very handy ratio rule. We can calculate the collector current for an arbitrary base emitter voltage VBE. Next, we will raise the base emitter voltage by a value of delta VBE and calculate the current again. If we divide the second current by the first one, we get this equation, which we can then rearrange to get delta VBE. Well equipped with our new formulas, we can finally revisit the common emitter amplifier. Previously, we got wrong answers for the voltage gain when we set the emitter resistor to 0. At this point, we did not know that the transistor has also an intrinsic resistance Re, which can be easily calculated by taking the derivative of VBE with respect to IC. It is also very common to state the inverse value of Re, which is then called the transconductance Gm. This intrinsic resistance must be added to the external emitter resistor and is only significant if the external emitter resistor is very small. If we now think back to our example from before, we get a finite gain of Rc divided by the intrinsic resistance Re for an amplifier with grounded emitter. Despite the high gain, this circuit is generally not a good amplifier. The extra gain comes at the expense of linearity, since the intrinsic resistance is dependent on the collector current. A varying collector current will therefore cause a varying gain and furthermore a varying input impedance. It is also very hard to bias, since the base emitter voltage varies with temperature. Therefore, it is better to add an external emitter resistor, even at the expense of gain. If you are familiar with control systems, you might like to think of this resistor as a negative feedback loop. The input voltage of the circuit is the voltage from base to ground. So the voltage from base to emitter is the input voltage minus the voltage drop at the emitter resistor VRE. A little increase of the input voltage causes a large increase of VRE and consequently a decrease of the base emitter voltage. Hence, the emitter current will drop, which again causes VRE to decrease. Negative feedback is commonly used to stabilize a circuit and is covered in one of our next videos. If you want to get the most out of a common emitter amplifier and want the highest possible gain for your AC input signal, you can bypass the emitter resistor with a capacitor. Now, on the one hand, the emitter resistor allows a stable bias point, which will adapt to changes in temperature. The capacitor, on the other hand, allows a low emitter impedance and therefore a high gain for AC signals. The common emitter amplifier is a standard example for voltage amplifiers. But there are a lot more important circuits to know, like the differential amplifier and the operational amplifier, which we will cover in our next video. For further reference, we highly recommend the following two books: The Art of Electronics by Horowitz and Hill, which is very informative as well as entertaining, and for our German-speaking viewers, we recommend Elektronische Schaltungstechnik, written by members of our institute. You can find the exact naming in the video description. So that's all for today. I'm Michael with the Institute of Electronics. I hope you've learned something, but anyway, thanks for watching.